But what is it? Okay, we get how fast it's going, but what is it? There's two trains of thought behind what is light. The first is that it's an electromagnetic or an EM wave, right? You would have seen this in the electromagnetic spectrum, which we'll cover here momentarily. But what happens is if you take a charged particle, right? So it has some sort of electric charge, and if you're able to get that charged particle to start moving a little bit, that means the electric field that it produces is going to change. And what we observe is that when you change an electric field, a magnetic field is generated. And as that magnetic field changes, because the electric field changes, well, it produces another electric field. And then that changes, which produces another magnetic field, which produces an electric field, which produces a magnetic field, right? And so on and so forth. So all it takes is you get an electric charge to start changing what it's doing, right? You accelerate it. And as you accelerate it, we can produce magnetic fields, which make electric fields, which make magnetic fields, and so on. And that's what this is showing us here in the diagram, right? We're seeing the magnetic field in red, or I'm sorry, the magnetic field in blue and the electric field in red. And as a result, no, magnetic field in blue, electric field in red. What we see is they're all perpendicular to each other. Right? So the electric field is always perpendicular to the magnetic field and vice versa. And the result of that is motion that is perpendicular to both of those fields. Because if you look, the electric field is moving up and down, the magnetic field is moving left to right, and then the wave is moving forward, right? If you look at your XYZ plane here, everything's happening in a different dimension, right? It's happening in a different plane. So everything is perpendicular in this situation. And here is your electromagnetic spectrum, right, which has been well established for, since the 1800s here, and even before that even. Radio waves to gamma rays, right, are electromagnetic waves. Radio waves, long wavelength, low frequency, low energy. Gamma radiation, extremely short wavelength, high energy, high frequency is what we have, right? So we go radio down to gamma radiation, so radio waves to microwaves to infrared to visible, which actually takes up an excruciatingly small piece of the electromagnetic spectrum, into ultraviolet, X-ray, and gamma radiation. Infrared and ultraviolet, they get their names. Infra is on the red side of the spectrum, right? Thus infrared, and ultraviolet, right? Violet is on the violet side of the visible spectrum, right? So those two terms, meaning under and over, tie in to our spectrum that we see. But again, if you look at your energies here, right, the higher your frequency is, the more energy you're going to have, the shorter your wavelength is, the more harmful it is, right? The more we consider a true radiation, the way that we don't always consider a radio wave to be a radiation, even though it's all around us and it's being produced constantly. Same thing with microwaves. You don't necessarily consider that as radiation the same way that we do X-rays and gamma rays, because X-rays and gamma rays, and even ultraviolet, I mean, you're aware, you go outside and you burn, your skin burns in the summer, but those higher energies are more apt to cause some sort of damage, unlike your lower energy waves. Speaking of energy, what we actually find is that even though everything's traveling at the same speed, we can still quantify the amount of energy that light has through this formula here. E equals hf, where E is our energy measured in joules. H is what is known as Planck's constant. It is 6.63 times 10 to the negative 34th joule seconds is the unit on that. And then F is our frequency in hertz. So because we have this Planck's constant here, if your frequency is high, your energy is high. If your frequency is low, your energy is low. And we already know based on wave speed, if you have a high frequency, you have a short wavelength. If you have a long wavelength, you have a low frequency, right? So we can start to see all of these pieces tie together here. So there's your energy. One way that we can prove that light is an electromagnetic wave was done by Heinrich Hertz in 1887. Notice Hertz, that's where we get our unit for frequency from. What Heinrich Hertz did was he was able to get a charge in a wire to move back and forth, right? So he was able to get this oscillatory movement of these charges going back and forth, and as he was getting those electric charges to move, what he found was that a magnetic field was generated. But he wanted to test what that field could do, so he put another piece of wire a distance away and tracked how quickly he needed to get those charges to move to create a magnetic field that could then get some other object to begin to move as a result of that field. And what he was able to discern was that this light was traveling at the speed of light, and it obeyed other characteristics of light already well known, such as reflection, refraction, and interference, but you couldn't see it, right? So there's no visible spectrum stuff going on here, yet he was able to prove that this could happen. Another proof that we see is diffraction, right? So the term diffraction is with any sort of wave, not just light, but any wave. If you put an obstacle in the way, that wave is going to somehow bend around it, right? So the bending of waves behind an obstacle. So picture a wall. Well, if you send water towards a wall, that water will eventually make its way around if it has the opportunity to, right? So waves are going to do this. Particles don't. Like just plain particles, like if you throw a basketball at a wall, that basketball is not magically going to hit the wall and then roll around it. That's just not the way that it's going to behave. Huygens principle is what we see to help describe diffraction. So what he did was he analyzed as waves came towards various obstacles, what happened before and after it hit that obstacle. So basically he would set up walls in different spaces and he'd have a gap in between, then he would widen the gap, and then he would just put one wall there, and then he'd put a wall in a different spot, and he would send waves at the same frequency and wavelength, and they would hit the obstacle, and then they would try to fill that space behind it. And the cool thing that he found was that the frequency and wavelengths of the waves before the obstacle matched what happened after the obstacle, which again helps prove that, hey, look what these waves are doing. And he could do that with visible light, and he was able to do that with different forms of radiation there. And then the double slit experiment is kind of the ultimate way of looking at light as a wave as opposed to light as a particle. So Michael Young in 1801, again, look at this, right? 1801. So he just had a window, right? And he basically put a barrier in there, and he had a narrow slit so that light could only go through this narrow slit after it came through the window. So he had this tiny band of light, and then he put a separate screen that had two really, really, really closely spaced slits. We're talking nanometers apart. We're talking a very, very short distance apart. And then the light would go through those two slits, the double slits, and then that light would pass there and then go onto a separate viewing screen where he observed, okay, well, what happened? So I focused some light from the sun, and then split it two ways. What is it doing now on this third screen? If light were a particle, there would only be two bright lines. Because think, the particles would have to choose one of the sides to go to. You can't take a tennis ball and throw it through two doors two doors next to each other at the same time. Like if you have a door on the left and a door on the right, tennis ball is only going to go through one door. So the expectation, if it was particle theory, would be a bright line in one spot and a bright line in the other spot, and that's it. Just two locations, because that's the only spot that you're letting those particles go. However, that's not what happens. What does occur is based on wave theory. So instead of seeing two bright lines, you see a series. So depending on how far you let it go, you're going to see 4, 6, 8, 12. You're going to see multiple lines, more than two bright lines that are back behind there.